Okay, welcome everyone to the fourth Plasma-PEPSC webinar. It is a great pleasure and a privilege to introduce today's speaker, Mr. François Mazen. François Mazen is the director of the scientific visualization team in Kitware Europe. Throughout his career, he has focused on developing software solutions for scientific communities from research to industry. This includes numerical solution methods, performance, artificial intelligence, and large software architectures. François is an open source enthusiast as he has been contributing to several open source softwares like the Debian operating system. Since 2021, he has led Kitware's European scientific visualization team. This includes team management, strategy, technical expertise he has, and also operational excellence and business development. Without further ado, François, you have the floor.
Okay, thank you, Jeremy, for this nice introduction. Okay, so today's topic is to discuss about data analysis and data visualization, especially with large data up to exascale data. I'm very happy to talk to your community today because I'm sure you have lots of challenges in plasma simulation to deal with, and I will be very happy to have some discussion and question and answer session at the end of the presentation. So shortly, yeah, Jeremy already introduced me. So I'm director of scientific visualization. I'm located in France. Sorry for my nice French accent. And so I spent all my career to develop software for scientists, actually. So mainly in industry and Siemens, and at Kitware for 5 years now. And I'm really into open source softwares. On many ways, I developed them for maybe 15 years or something like that. Okay, so today I'm part of Kitware. I have few slides about the company, and then I will move to the technical part. So Kitware is quite a small company, 230 employees worldwide, mainly in the US, and there is one office, outside of the US, which is in France, in Lyon, in the nice city of Lyon, with what we call Kitware Europe, actually. There is about 35 people in Lyon. So what do we do is we develop open source solution for science and AI, mainly about data analysis and data visualization. So here are some platform we develop. We have about 40 to 45 products actually. So here are the big names you probably know. So ParaView for today, VTK, TomVis for tomography, ITK for medical imaging. We have also CMake, which is our biggest product, in order to configure some C++ build. It's developed actively by Kitware for many 20 years now, something like that. And we call our software more platform because as they are open source, lots of people are reusing them in order to build largest applications. So there are more framework and platforms than just softwares. In the topic of data analysis, we have several flowers at Kitware. We have people specialized in computer vision, which is basically to be able to post-process data from sensors. So it could be from LiDAR, radar, sonar, from satellite imaging, also GPS and so on, be able to aggregate everything and do some analysis, some detection and so on. We have lots of solutions about data and data analytics in the classical way, big data. We have scientific computing, scientific visualization. This is the topic of today, and you can see some nice ParaView rendering here of turbulence behind a plane wing. This is a simulation. We have a team dedicated to medical imaging. This is very specific topic. With a solution which are widely used in this area, like 3D Sizer or ITK. And we have software solution. We see everything around CMake, because CMake is a big ecosystem with CDES, CPASC, CDash, in order to manage software lifecycle with continuous integration, continuous development. So we have lots of expertise in this area. And the question that everybody asks, how do you make money with free software? Okay, indeed, we do not sell the software itself because they are open source, freely available for everyone. So Kitware is basically a consultancy company. We provide services. So from Kitware, you can get some trainings, how to learn how to use ParaView or ParaView Catalyst. We have some training. ParaView also support if you need to get access to some experts in our team. If you are stuck, if you have some question or need some advice, we can also provide some consulting on your code and so on. We do development, of course. Software development is the core of our expertise. We can either develop new features, something which is missing in our solution. I don't know, in PTK you need some new features. You can ask Kitware to develop it. Or we also develop a lot of custom applications for customers, which are usually not open source, only for the customers, but based on our open source platform. So basically, a ParaView-based application for plasma post-processing, for instance, or a VTK-based application for electromagnetism workflow simulation, and so on. This is this kind of application. And the last thing, we do a lot of collaboration with university and academics. So this is usually with some public grants. So in France, we have some specific grants for that, or European grants. We do a lot with researchers in order to be connected to the state of the art, and also ask Kitware to push research results to industry through the open source frameworks in order to make it available to everyone. So I know that today there is likely lots of researchers in the room. So if you want to collaborate with Kitware for your next grant, do not hesitate to contact us. We are very happy to be part of some large projects where there is some data and visualization challenges. So that's it for Kitware. Let's move to scientific visualization. This is the topic of today, of this webinar. So what is scientific visualization? This is basically the idea of, from your scientific data, to be able to display something that has some meaning for you as scientist or engineer. And in order to display the things, this is basically a two-step process. The first process is a processing process where you want to extract some features, so extract something that is meaningful for you as a scientist. So in this very basic example, we can just need the external surface of a dataset, or to compute some ISO surface, or maybe compute just some number, like some statistic on the value in your dataset. And then you have the second step, which is the rendering step, where you want to display the results on the screen. So basically to generate some pixels on the screen. And in this step, you also have several choices to do how to display it properly, using some, I don't know, volume rendering, some triangulation rendering, some wireframe rendering, some graph and plots and the whole process. This is scientific visualization. So just bear in mind, in the next slide of my presentation, we will talk about large scale and large data and so on. And for these challenges, we will have to scale the two steps: the processing step, just to compute things on your data, and also the rendering step, how to get pixels on the screen. So when you just to start, some nice rendering, some nice scientific visualization I wanted to showcase. I hope it's not too laggy on your side. So what we're looking at is SPH simulation, so particle simulation. There is about 2 billion particles here rendered, and the author did some choice in order to get this nice visualization. Just for the context, it has been rendered by CSCS on the ALS machine, so in Switzerland, so close to Europe and to the French office. So if we do a stop motion on this particular picture, for instance, so the raw data are a point cloud, so particles. So particles with some fields on each particle, which is maybe temperature or entropy or enthalpy or anything, something that is meaningful for science. And here the author did some interesting processing. So first they cut the data set, so in the processing phase, in order to see inside only one half. They also create some slice, and they put the slice on the bottom. This is the ground here. Actually, this is a slice inside the particles. And then on the rendering side, they also did some interesting choice. They use ray tracing in order to get particles on the coalescence of these astrophysics simulations. And they also use some volumetric rendering here in the image on the bottom in order to. So volumetric rendering, this is a techniques basically used usually, which is very popular in medical imaging in order to see inside the volume, usually inside some insight of how the phenomena and how the core of Jupiter is working. So this is a very good example of scientific visualization, how from a point cloud you can get some really meaningful data. And if I put again the video here, I don't know, how we can study the core of Jupiter, how it behaves, and so. Okay, and this nice visualization has been rendered with ParaView and processed and rendered with ParaView. So let's talk about ParaView. If I want to talk about ParaView, I have to talk about VTK. So VTK is the library behind ParaView, actually, VTK does most of the work. So VTK is a library, 30 years old, maybe more, so 32 this year. It's actively developed. So this is a library to do scientific visualization. So to do the two-step I presented before, and to generate some nice images. So it could be classic scientific images with some color mapping, or to do advanced rendering, like here with this nice car, and we can see some isosurface of the cube criterion, and of course it's rendered with very ray tracing algorithm. So this is VTK, and on top of VTK we have ParaView. So ParaView is an application with a graphical interface in order to first exploit VTK, to apply filters on data source and so on, and to add distributed rendering, which I will detail later, in order to tackle very large data and be able to, with the client-server architecture, to run the server on a supercomputer and be able to open very large data and to analyze very large data. So this is the interface of ParaView. If you don't know this software, so this is multi-view. You can display either 3D rendering, either table, either plot, and you have the pipeline browser in order to manipulate filters and data and so on, and some properties. So it's very handy to use and very interactive way. There is lots of features. I won't cover them today, of course. Just get some training from Kitware if you want to know more, of course, about ParaView. But this is a generic tool to analyze and post-process data and to get insight from your data from the scientific perspective. So it's widely used in the scientific community, from industry to research. Most of the top 500 supercomputer use ParaView. This is really part of the classic software stack, which is installed on an HPC. And this is ParaView and VTK are really actively developed by Kitware, and also thanks to the open source community, also by external contributors, mainly on the connectors, some specific file connectors. We have people outside of Kitware developing them. And Kitware guarantees the stability and the performance of the core of the application, and to integrate external contribution inside these core features. And ParaView is not just a software. This is a whole ecosystem, actually, because thanks to the client-server architecture, you can interact with your data in lots of ways. So the classic ways is to use the desktop client. Maybe you already know it, but there is lots of other bridges to interact with your data. For instance, with web application like ParaView Web or Tram. Also, everything is scriptable with Python in ParaView, so you can automate everything. With Python comes the whole Python ecosystem, so you can do some machine learning in ParaView with PyTorch or TensorFlow, for instance. We have connectors to more fancy visualization with virtual reality, augmented reality with OpenXR. Also to interact inside your Jupyter notebook with ParaView to stream the data to your Jupyter, the rendering to your Jupyter notebook, and also in situ visualization. I will talk about it shortly. As I said, ParaView is generic, so there are lots of domain. It's not tied to a specific domain, and you can use it very broadly to post-process your data, from experimental like medical up to simulation, astrophysics, geoscience. Yeah, some nice use case I like to display. For instance, the IPCC report, for the global warming. Most of the 3D rendering are made with ParaView by the DKRZ Institute in Germany. And they tackle very large data, usually several petabytes of data with their supercomputer to generate this nice visualization. And few words, we collaborate a lot with hardware vendors, for instance, NVIDIA. So you have some connectors with Omniverse, also to get access to the low-level rendering library of NVIDIA, like Index or Optics. And we also partner with Intel in the same way to foster their software stack on top of their GPUs and CPUs, like Osprey for ray tracing or TPB for code parallelization. And just my last slide about ParaView. As I say, you can easily integrate PyTorch for machine learning. So there is already some big names using ParaView in order to run some inference of your neural network inside ParaView. So if this is something that you are interested, yeah, do not hesitate to experiment and also to reach Kitware if you're interested in this specific one. Okay, so let's move to large data, exascale data analysis. I don't know if you can interact, but could you tell me, for you, what is the first challenge you have to tackle when you have to analyze and visualize your data at exascale? You can put it in the chat or just speak up if this is possible. I don't know, Jeremy, if this is possible.
Yes, it's possible to put in the chat, but I can maybe assist that help you about. One of the biggest challenges is parallel I/O or I/O. That's one of the biggest.
It could, yeah, kind of.
And what about scaling across some very large systems? That may be something in stream scaling, data processing, and how to optimize it. There's no handling it.
Yeah, definitely. So I/O and the architecture also, the system they are part of the challenge. So I will go on. So the first challenge I want to talk about is linked to I/O. This is the data size.
Yes.
Because with exascale system, you have very large simulation. You want to simulate with a smaller time step or smaller mesh increment and so on. So you generate very large data size. So having petabyte of data is very common. So basically, there is two ways from your numerical simulation. The first way is, okay, my data are not so big. I can write it to disk, and then I will do some post-hoc analysis. Once it has been run, I will open it, of course, with ParaView in order to analyze and visualize it. And the other way is, okay, the data is too big. I have petabytes in memory or maybe terabytes, but I do lots of time steps, so I cannot save everything to disk. So in this case, we will be able to leverage in situ analysis. So in situ analysis is the ability to be able to process live while the simulation is running. You connect some co-processing, some analysis rendering, in order to reduce the data with the data inside the memory, inside your simulator, and you write to disk only the data reduction. And of course, once you have reduced your data, you can also do post-hoc analysis. I will show you later. So let's talk about the first case. You have some data on your disk. They are large. They are very large, and you want to leverage ParaView. So ParaView has a client-server architecture, as I said. And on the server side, there is two servers, the data servers and the render servers. So if you remind the scientific visualization basics I presented, you have the processing step and the rendering step. So data server is for the processing step and render server is for the rendering step. Very, very simple. So when you launch ParaView on your local machine, everything is packed together, is transparent for you. But what is interesting is that you will be able to run the data server and the render server to another machine, to either, of course, a supercomputer or maybe a big machine in the lab, and be able to connect your client to this server and only stream the result of the analysis and the rendering. So just only stream images actually. So this is very convenient how to open very large data. And of course, if you have some very advanced infrastructure, you can separate the data server to run on CPU and the render server to run on GPU, and to make everything work together to exploit the power you have on your infrastructure. And we can couple everything with in situ analysis, as I will demonstrate later. So when you run your server on a big machine, you can use MPI in order to do distributed analysis and rendering. So basically, ParaView work by domain decomposition. So basically, you have to cut your geometric domain in subdomain, and each node will load only the subpart and work on the subpart. So they will do the analysis, so compute an isosurface, for instance, only on the subpart, and do the rendering also on the subpart. And it's very easy to launch it. MPI run, number of nodes, PV server, and so on. And if you are on an HPC with Slurm, it's very easy to integrate. In this basic example with 4 nodes, for instance, how does it work? So each data server will load the subdomain, compute the isosurface. If you ask for an isosurface, of course, if this is a slice, it will compute a slice, and so on. Then the output of the isosurface will be sent to the render server in order to create the picture only on the subpart. So at the end here we have 4 pictures, and the first rank will compose everything with some smart algorithm in order to aggregate and create the final application, final image, which will be sent then to the client. So basically, in this case, if you have some volumetric data, here each node load the data, compute the isosurface, then create the images, so the 4 images on the top, and then everything is aggregated, of course, with some depth buffer in order to know what pixel is in the front and the back and so on, in order to create the final image. So this is how ParaView works. This is how you can tackle very large data. So we have some record with tens of petabytes now at Exascale simulation, and be able to post-process them very easily. Of course, you need the computation power in order to open all the data at once using a multi-node application. So then short parenthesis around how to connect your client to your HPC, because in supercomputing world, the HPC are usually the access to HPC is really very controlled. So the first thing is to use SSH, but you have to open some extra port when you use a client-server architecture. So you have to create some SSH tunnel or to use reverse connection, and this is not always possible. Usually the system administrator doesn't like it because it creates some potential vulnerabilities. So SSH is okay for your lab, but it's not okay for a supercomputer. So what we see is usually you have some dedicated graphical node on the supercomputer, and you connect to them with a specific system, specific remote desktop, like NiceDCV or similar thing. It's okay. You still have to launch your ParaView with Slurm, with your PV server and so on, and to connect. So still have to some manual step, but it works. It has also some drawbacks because you are on a remote desktop, so it's not always responsive, and you still have to sometimes to get the data back to your local machine and so on. Oh, okay, it's not the best, but it works. This is very common in the HPC world. And last one I want to present today also, we see more and more web platform in order to access to your data. And Tram is one solution we develop at Kitware. And what showcase of this is what the software stack team have developed at Jülich in Germany. They develop a whole stack, a whole application, based on Tram. So Tram is a framework to build some scientific web application. And they wanted to automate how to launch the ParaView server on the visualization node, and how to learn a Python client and to stream the image back to the web application. And they succeeded, and it's quite impressive. So I really encourage you to look at the blog post we published on it. And we see more and more of this application in the HPC world in order to get an unified access to ParaView and to visualization. And the scientist doesn't have to work with Slurm and SSH anymore, thanks to this web application. Okay, so we discussed post-hoc visualization. Let's talk about in situ with Catalyst. I think we have to be a bit faster here. So the idea is to connect the simulation to a module which will run the analysis with the memory, with the data on the memory from the simulation. And so the solution in ParaView is Catalyst. So this is a classic example, rotorcraft simulation. You have half a gigabyte for each time step. Imagine you want to run, 1,000 tab set. You can generate very large data. But actually, as a scientist, you just need the pressure on the blade, for instance, as an engineer, because you want to optimize the blade. So maybe you can just save this on disk thanks to some in situ technique. And even if you want to do very big data reduction, you just want to generate the images, because images is just enough to understand the phenomenon. And in this case, for each time step, you move from half a gigabyte to less than 1 megabyte. So it's very powerful to do data reduction. Another handy techniques with in situ is to get more output with very large data. Sometimes when the data is large, you can still save it, but not on every time step. So you save it maybe one every 100 time step, for instance. So you can increase the frequency and not save the whole domain, but just a reduction, just a picture, or just an ISO surface, or just some slice, just to check. This is very handy for debugging, for instance. And in situ is a whole ecosystem. There is lots of solutions, as you can see here, with Ascent, Catalyst, Lipsim, Sensei also. So today I will of course focus on the Kitware solution, which is ParaView Catalyst. So ParaView Catalyst, I will talk about the Catalyst 2. There is Catalyst 1, which is the legacy one. I do not encourage to use it. Please use the new version. So this is a very light way to connect your simulation to some analysis. It's not tied to ParaView or to VTK. It's really independent. And there is only 5 methods, and only 3 are mandatory. You have to call catalyst initialize at the beginning and finalize at the end. And each time in your simulation you want to run some coprocessing, some analysis live, you have to call execute. And if you want to do some steering is a two-way communication, which means to send data back to your simulation from the analysis. For instance, in your analysis, you detect some criteria. The pressure goes below a threshold, and then I want to change something in the simulation. You can do it with in situ techniques, and the catalyst results is here for this. So basically, how does it work? So you have to update your simulation code to create a small adapter. As I say, it uses a conduit node, which is a description of the memory. This is 0 copy. You don't have to copy your memory to something. And also you have to prepare the analysis you want to do. So this is a classic ParaView Python pipeline. So very easy if you are familiar with that. So you can leverage all the filter you have in ParaView. If you're using some very specific thing, I don't know, with temporal, pass line from particle and so on, you can use it with thanks to this Python pipeline. And then at runtime, you just provide the pipeline to the adapter and provide a catalyst implementation like the ParaView one, and you will be able to, on the live, generate data, screenshot, and anything you want. What is very interesting is that it's very flexible. You don't, if you want to change your in situ analysis, you don't have to rebuild your simulation code. You just have to provide another Python file. For instance, if one scientist want to check a specific thing in the dataset and one other want to check another thing, they just have to provide two different Python and run their own simulation code the same, and they will get different output. So it's very, very powerful. Yeah, and some showcase here. It has been generated by Chineka. So here they are simulating 30 billion points. So it was not possible to save it on this. So they generate some ISO surface live and save only the ISO surface to the disk with the associated data, and they were able to create some impressive visualization like that and to understand how the turbulence works and so on. So this is in situ analysis, very powerful. This is really mandatory in Exascale simulation because you cannot save everything on this. But there is some drawback actually. If we look at this time flow, we can see at the end of the simulation step, we launch the analysis, then we resume the simulation step, we launch the analysis. So the analysis is a blocking call, actually. So it could slow down the simulation and create some problem. So we develop a new approach, which we call in transit. So the idea is, instead of doing the analysis on the simulation node, we will do it on another set of nodes that we will call visualization nodes. And we will have to transfer the data from one cluster to another. And for this, we use Adios, a library in order to move data very efficiently. So if your simulation use Catalyst 2, you can change on the fly at runtime the implementation and use Catalyst Adios in order to push your data to another set of nodes and do your analysis on another node. So this is very, very, very powerful also. And but there is one drawback if you are following, because at a large scale and exascale, you have potentially, I don't know, petabytes of data in memory, and you don't want to move 1 petabyte from another cluster to another. This is not possible. This is very costly. So we develop a third approach, which is what we call hybrid. When you do in situ data reduction on the simulation node, the green box here, and then you stream on the visualization node only the reduced data. So for instance, you resample on a coarse grid, or I don't know, you create some 10 slices, and only the slice you send it to visualization node for either saving to disk or creating pictures and so on. So this is very, very, very powerful. I really encourage you to look at it. And on this topic, also, we are facing a classic problem, which is, okay, we run the simulation on a very large computer, exascale machine or petascale machine. But for analysis, we have a smaller machine actually. And it's not possible to load every data at the same time and so on. So we are working also on different approach, which is progressive analysis, for instance, which is to work on data on a progressive way to compute as a scientist compute your feature in progressive, first with coarse data and then to refine iteratively, or to work also with out-of-core techniques to load only on demand what you will need to do the analysis and the random. This is to another way to where we are working with researcher. Okay, so it was the first challenge, a big challenge about data scale. And Jeremy just mentioned before the architecture also. The system is also a challenge. So this is my second challenge I want to demonstrate here with the hybrid architecture. So nowadays, big machine, nowadays computer are highly hybrid, CPU, GPU, APU, something PU. For instance, here we have the three biggest in the world, El Capitan, Frontier, and Aurora. And they have basically the same high-level architecture with each node has a bunch of CPU and GPU connected together with shared memory and so on. So how we can exploit this for scientific visualization? So we are facing several challenges because there is parallelism everywhere from the CPU side, from the multi-CPU side to the GPU, also on the file system side, and of course on the multi-node side. So we have lots of scales of programming. So for scientific visualization, so I already discussed the MPI techniques with ParaView for multi-nodes. But for inside the nodes, in order to exploit all the power, we use Viscores. This is a new name of VTKM. It changed their name. So this is a rewriting of VTK of specific filter, of VTK, in order to tackle heterogeneous architecture, many core architecture. So basically, if you want to compute a contour on a recent supercomputer, it's really great to leverage Viscores, which use as a backend either some CUDA, some Cocos, or some OpenMP, in order to get the most of the power of the many core you can get on the supercomputer. So in ParaView, it's very transparent. You just have to activate the VTKM plugin, and everything is replaced, and the filter are replaced live. So it's very easy to use and very powerful. And if we combine in situ with VTKM, we have now some nice workflow where, for instance, I keep some French word here. Simulation numérique Exascale. So this is Exascale, a numerical simulation, where you can keep the memory on GPU, because lots of new codes works on GPU only in order to leverage parallelism. And you can do in situ with Catalyst by keeping the data on GPU, and also do your analysis and rendering also on GPU. So the data do not move to the main memory at any time, and you can use the main memory and the CPU to doing other things. I don't know, to saving on disk and so on. And of course, with Adios, you can also do in transit. There is a special mode in Adios to do memory to memory copy. So this is very innovative workflow. So if you are also interested in working on it, please contact Kitware. We'll be very happy to help, or even to develop new technologies if something is missing. Okay, I still have 5 minutes. For the third challenge, I want to talk to you. This is more specific. At the moment, we again remember the scientific visualization basics, so the processing side and the rendering side. So for processing, we have lots of things. We have VTKM, we have the MPI parallelism, and so on. But for the rendering side, at the moment, it's quite complex. We have some challenges with the graphic API. So graphic API is the API we will use to get pixel to the screen, or get pixel to a buffer if there is no screen. So we have a bit in a crisis at the moment with HPC graphic API, because OpenGL is end of life for 10 years now, but we still use OpenGL. It still works, so do not worry. But it's still missing the new feature we can see on modern GPU, and there is no clear replacement for this. And the other thing is that the GPU in HPC, in supercomputer, actually they are not GPU. They are not graphic processing units. They are AI processing units made for to do tensor multiplication, tensor operations. But they do not have the rasterization. Rasterization is the ability to transform triangles to pixels, and so on. And if we want to leverage this new GPU, we have to use a low-level vendor library like AMD Radeon or NVIDIA vRTX and so on. And it's very complex. So we have to adapt for each hardware. We have to adapt the code. So it's very costly. And most of people, what do they do? People who are very pragmatic, they do some OpenGL emulation on CPU. So you have big machine with big GPU, and finally you use a CPU emulation. So this is really a disaster at the moment to be forced to do this. So of course, Kitware is working on a solution, on several solutions. I want to shortly display here. The first one is Anari. Anari is a high-level rendering API, which tries to talk scientific visualization. So it talks about mesh, about field on the mesh, about ray tracing, and so on. But it doesn't talk low level how you will render things. And you can delegate the rendering to low-level API in order to leverage HPC GPU like the AMD Instinct and so on. So it's a very powerful API. We are really working on it and pushing to ParaView. We hope that the upcoming ParaView 6.0 will get it, but maybe will still be prototype. But this is really the future. And another way we work also is Web GPU. So there is web in the name, but it's not linked to web technology. It's quite generalized. This is a high-level abstraction of the GPU. So it's not as high as Anari. It's more low level, but you can access to release a new native API of GPU. And for instance, we have some showcase here where we develop some specific rendering for point cloud, and we were able on a classic workstation, no fancy hardware here, we are able to render 2 billion of points and to be interactive, so really with the mouse. It's really real time here, the video. So this is really promising. Okay, I think this is my last slide. So I talk about large scale, exascale data analysis and visualization. I hope you learn a lot. Just a sum up and a takeaway. The challenges are first data size. For this, you can leverage ParaView. It's really the perfect tool for this with MPI protocol in order to do distributed analysis and visualization. And if your data are too big, too large, use in situ and intrinsic technique, and Catalyst is also the way to go and to leverage the whole ParaView ecosystem behind your Catalyst adapter. The second one is the hybrid architecture. You have CPU, GPU, FPGA, I don't know what, and you want to use it as much as possible in order to speed up the rendering and the analysis. Viscores VTKM is really the way to go for scientific analysis and visualization. As the last one, this is a graphic API. As I say, it's quite complex to really have access nowadays to the new GPU, and there is some new API I've just talked about. And as a conclusion, I will say we are Kitware. We develop open source. We are really close to the research. This webinar is also a request for collaboration. So if you are facing any of these challenge or other challenge links to data analysis and visualization, please reach us, and we'll be very happy to understand, discuss, and maybe collaborate and develop new technology together. And when Kitware develops something, usually it goes to open source, and the whole scientific community could benefit from it. So this is really a great way to collaborate with Kitware. Okay, thank you for your attention. I hope you learned something today. I'm open to, we have 10 minutes for question or discussion.
Yes, perfect. This is great. I was very intrigued. Thanks so much. So what I'll do, to the interest of time, I'll start off with one question, and then I'll start to ask some persons in the call maybe some interesting one. One of the things of our project, we want to enhance our codes to Exascale. So one of the things that most everyone on the Konos are quite interested in is what is the main challenges ParaView face when scaling to exascale systems, and then how is it being optimized to handle extreme scale data processing? Because I've seen you use Exascale systems in the US, and you have a lot of experience with this. So maybe you can give us some enlightenment there.
So my question: what are the challenge? The first challenge you are facing, right?
Yes, what'll be the challenges ParaView will face? It's so you're using ParaView. Maybe we can comment more on the challenges you experience when scaling to using Exascale machines, and then during that process, how you're optimizing it. What will be the best process approach to optimize this process in handling extreme scale data processing?
Okay, so actually, the first challenge you have is just to be able to launch ParaView.
Oh yeah, that's true.
Yeah, definitely. And the third challenge I've talked about graphic API is really part of the equation, because with ParaView you have several flavors with graphic API. Either you have some GPUs and some OpenGL context you can use. Sometimes you don't have them, so you have to use some EGL or Mesa variant of ParaView. So this is the first challenge, to know what to use and what to deploy, and then to be able to actually install it and deploy it using NPI on very large data. And once it runs, it works. It works because ParaView is very robust. It works for 20 decades now. So yeah, this is I would say this is the first thing, being able to deploy it correctly and to get the most of your power of your Exascale machine. Yeah. Actually, you mentioned the US project.
Optimizing. Yeah.
Yeah, with the ECP. They didn't have the nice graphic API, so they had to use Mesa, so some OpenGL emulation, to do some nice rendering at Exascale, which is quite a pity actually, for the rendering to not be able to exploit the GPU. So this is really the first challenge actually, I would say.
And that brings me to my next question, because of these challenges they've experienced, maybe scientists or specialists will need to, or domain specialists need to do some changes. So, what options does ParaView provide users to develop like custom plugins or scripts to handle this process, and also how this can be extended to enhance the domain-specific visualization task in this case? So, in case sometimes you'll have ParaView will have everything in the ready for you, but then maybe you need to change the scripts in such a way, because I know you mentioned Python, right? So there's a way to maybe change the flow or the workflow.
Oh, this is a really great question. Thank you. Yes, I did not mention it clearly, but yeah, ParaView is really more than just a software. This is a framework, so you can extend it very easily in many ways. So there is very light ways with some Python plugin, of course. As I say, everything is scriptable in Python in ParaView. So you can either write your custom filter in Python, or to leverage some Python libraries underneath. And of course, and there is lots of there is a macro system in ParaView where you
Yes,
can automate
exactly.
on the client side. As the scientist, you always do the same, I don't know, 5 features that you apply to your data. So you can create a macro, record it, and then with a button, select your data, click a button, and the file feature are applied automatically. So this is very handy. And then yeah, you can extend with plugin if you have very specific needs. So Python is for very innovate things. You just want to, I don't know, to do some PyTorch things or things like that. And you can also develop in C++ some plugin if you really want to go into performance. I don't know if you want to create a reader for your specific data, or I don't know, to do some specific yeah, I don't know, computation on your data, and you really want performance, or to plug to specific libraries.
Okay, so we have a question, Stefan.
Yeah, Stefan.
Hello.
Hello.
Will there be support to load an SST file from Adios 2? So it's a stream file, and to capture the stream directly into ParaView without using Catalyst?
At the moment, you can open for Adios, you can open a BP file, which is the file which is generated by the SST engine, if I'm not mistaken. And you have several ways. There is a reader for maybe 5 years or something like that in ParaView, where you can open your BP file, and you have to add a JSON file in order to describe how your data are organized inside your BP file. So if you are streaming things, and then if you are really streaming things, there is a plugin called FIDES, FIDES, which allows you to open a stream from Adios and convert it to VTKM and then to ParaView rendering.
Okay, thank you.
You're welcome.
Do you have any other questions for anyone?
Yeah, Leon, I would like to ask why this VTKM is not yet included in ParaView. Is there any intention to completely replace with this multi-core VTK everywhere, or is this, let's say, a problem that we are using Python and that will not get ads easily, or why VTKM is not being widely used in, let's say, applications directly? Is that problem with, let's say, many different approaches for this multi-core, so it's difficult to compile for the target architecture, so it's not portable? So I wonder what is the intent of VTKM in ParaView or elsewhere to be replaced, because now we have multi-core everywhere. So I would say that VTK should be replaced by M.
Yeah. Well, there is some answer in your question, so thank you. First, VTKM is part of ParaView, but you have to activate it via a plugin. But we ship it by default in our binaries first. But you're definitely correct. VTKM use backends, and the backends depends on the target architectures. So we cannot. So what we provide by default is some many cores with OpenMP or TBB, something very generic. But if you have your own architectures and you want to tune it with Cocos, for instance, or directly CUDA, you have to build VTKM yourself and activating the right options and so on. So we cannot be generic here. You know, in the HPC world, each supercomputer is very specific. You have to activate lots of options. Hopefully, with MPI and MPitch, we have some high-level compatibility. But for low level with many core, we cannot be generic here. And the second part of your question, why it doesn't replace VTK? First, VTKM doesn't implement every filter from VTK. VTK is very large, and VTKM is really as a small scope, actually, which targets large-scale simulation. And also the way VTKM is implemented, it has its own data structure, so there is an extra cost when you have to convert from one word to another. So it's not made for the generic approach of ParaView. It's very too specific to be part of the vanilla ParaView, actually.
Okay. Thank you so much, Leon. It seems like we're out of time. And also, I'd like to thank you so much, François, for the option to give us this very excellent insight. If there's any other questions? No other question? Okay, so I close the session.